in our last section of chapter 2, section 2.8, one-to-one functions and their inverses. So the idea here is that we'll first start with the idea of what an inverse is. So two functions are considered inverses of each other if, when you compose them with each other, you get x. So in the last example from section 2.7, we saw two functions where when we compose them with each other, we got x each time. That is the definition of what it means to be an inverse. The notation that we use for inverse looks like this. So notice it is simply that we have this little like -1 up at the top, but it's not an exponent. So of course the key thing to see here is, you know, if you had something like x to the -1, that's 1 over x. So this is not like a -1, like I understand that that's what you're seeing, but it's just the notation for inverse. It means this is the inverse of something. So as an example, we actually already saw this. These two functions are inverses because f of f inverse composed together is x, and f inverse of f is x. We saw this in the last section, but instead of f inverse of x, it was just called g of x in the last one. But now that we know that they're inverses, we can call one f of x and one the inverse of f of x. So graphically speaking, it's kind of interesting to see a function and its inverse graphically. So if you take a look at the graph that we have there, it's just the line y equals x. So just know that this is the identity, linear identity here, y equals x, linear function. So let's graph these. You are welcome to pick some values and graph them each yourself and see what they look like, and then I'll talk about it. You know, you're more than welcome to do that. You don't have to wait for me. If you want a little bit of help, I can give you some x values that I chose. And I'll talk about why, but we're just gonna graph these two lines. So again, you can do that any way you want. If we plug in these values for x over here, it looks like we will have this. Okay, so let me put those on here. Both of these are lines. That's a good thing to remember. They're just both lines. So -1, -3, 0, -1, 1, 1, and 2, 3. Okay, so here's one of them. Okay, go. Okay. And then with the other one, what I might do is just, I'll use a different color here so you can see that. Try to keep it consistent. So I'm using -3, -1, 1, and 3. Again, the reason I'm using this is because I'm dividing by 2. So I'm trying to pick numbers that I can easily divide by 2. That's why you see those values. It is just a line, so you can easily find by choosing the kind of values that I did, y values that are not fractions. So I'll have -3 and -1. I'm going to have -1, 0. I will have 1, 1. And I will have 2, 3. Nope, 3, 2. There we go. Okay, so here's my other one. Dun, 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 dun. And then down here. Okay. Okay. So it may not be obvious to you right now, but there is actually a relationship between these two lines over the line y equals x. So what you should see is that, and you can actually see it, I'll have it on the next slide, but if you look at the note in the notes right under this graph here, it says the graph of a function and its inverse are symmetric about the line y equals x. So if the point AB is on one graph, then BA is on the other. So you can probably see that now that you see the points that I have chosen here, but notice that the points that I have are just flipped from one to another, one of those functions to another. So thinking about that, I mean, it literally just means if we have -1, -3 on one, we're going to have -3, -1 as the point on the other. And then that creates the symmetry over the line y equals x. So if you're ever asked to graph a function, all you really do is have to graph one of them and then just flip all the points, and then you get the graph of the other. So that's kind of a really cool thing about inverses. So there it is, what I was just reading to you. If two functions are inverses, you have a comma b, so you're going to have b comma a on the inverse. Okay. Now, you might think, well then, I guess all functions have inverses. No. Not all functions have inverses. In order to have an inverse, you must pass the horizontal line test. So remember, every function passes the vertical line test already. It has to pass the vertical line test to be a function. If it also passes the horizontal line test, then you have a function that can have an inverse. Okay. So we have, looks like my little a here. A, you have it in your notes, but that should be, a nice A. So the horizontal line test is just like the vertical line test, except it's horizontal. So vertical line test, we only want to cross in one space. The horizontal line test, again, we only want to touch in one place for any horizontal line we can create. So we create a horizontal line here, we intersect one time. We do a horizontal line here, we intersect one time. Horizontal line here, we intersect one time. So as long as we only intersect one time for any horizontal line we can create, we have a one-to-one function. So as you can see, this one is, yes, this one is 1-to-1. 1, 2, 1. Okay. Now, the other one, you might be able to see pretty quickly that this function is not 1-to-1. So yeah, it's a great function. You might recognize it as, it's actually a parabola. As you can see, it's actually 1/4 x squared is the function there. It's kind of weird, but that is the function, 1/4 x squared. But you can see very quickly that it doesn't pass the horizontal line test. So it is not 1-to-1 as it is right now, not 1-to-1. But I'm going to make one little caveat here, one little side note, which is there is something that you can do. You can restrict a function. If you can restrict a function so that the domain that you have it on is 1-to-1, you can find an inverse for that. So if we were to restrict, so just as a side note, let me write that here, side note. If we were to, we can restrict the domain to x being greater than or equal to 0, then we can end up with an inverse. So the idea would basically be to half that parabola, put it in half, and then find the inverse for 1/2 of it. So I'll just put one more thing on here if you want me to, but if we were to, let me go, just take this part of the graph, and you can see that that part by itself would be 1-to-1 because of the symmetry. So if we just take half, we could find an inverse for that part. So it's not that it doesn't have one, but you would have to be able to restrict a domain so that it is 1-to-1 on that domain. Okay, so let's talk about how to find some inverses. Let's see. All right, so you have the steps here for finding inverses. And it's pretty straightforward. It just requires, some algebra once you do the steps. But typically speaking, if you have a function and you want to find the inverse, if it happens to start with f of x, it can, because of the work that's involved, it can be easier just to write it as y, just so that you're not writing f of x, f of x, f of x. It's a little easier just to see it as y because it is the output, and then just replace it back in the end with the inverse notation. So first step, make sure it is y. Then the second step is to interchange x and y. And you can kind of think about this logically because you know that every point graphically on a function and its inverse is the x and y are flipped. So we're going to flip the x and y and then see what we get when we solve for y. So we get x equals y cubed plus 1. We're going to solve it for y. That's going to give us x minus 1 equals y cubed. And then I'm just going to flip it around. I'm going to take the cube root of both sides. So the cube root of y cubed, that's the idea there. And so that's going to give me y equals the cube root of x minus 1. So that is the inverse of x cubed plus 1. So there you go. Now, I still need to kind of like finish this off here because I want to say I have an inverse. This is my inverse. Here it is. So here's my inverse notation so that I have that. Ta-da. There you go. Now, a couple things to understand is we've seen x cubed plus 1 before, actually. So we saw it back in section 2.6, I believe. So with x cubed plus 1, I'm just going to make a note here. X cubed plus 1 has a domain of all real numbers because x cubed has a domain of all real numbers. It's a polynomial. So adding 1 to it, it still has a domain of all real numbers. Its range, if you think of it, you put large negative numbers. I should do this way. You have large negative numbers, it goes negative. You have large positive numbers, it goes positive. So this function runs the gamut of values up in the y direction and down in the y direction. Because of that, the range is also all real numbers. Okay, so the reason I say that is because it means, this is what it means. And this is the note at the bottom of the page. But a function and its inverse will have opposite domain and ranges. Now, it's not very exciting for this one because the fact that the domain and range are all real numbers for both mean that the domain and range, the domain and range is everything, is all real numbers for f of x, so it's going to be the same for the inverse. But let's look at the next one. So see if you can, it would be really great if you could pause, see if you can do those same steps and find the inverse for the next example that we have. I'm going to do it here. So I need to replace with y 2 times. So don't forget that. You can't just replace it once, you got to replace it both. And now I need to solve for y. So I'm going to multiply both sides by y plus 4. Okay. Then I'm going to multiply through by my x, use the distributive property. Now, if you haven't paused so far, you should definitely pause and see if you can solve this for y now. That would be very smart. So the key here is because I see y twice, I'm going to bring everything with a y to one side. And if it doesn't have a y, I'm going to bring it to the other side. Then I'm going to factor. That's pretty much the key here, is because I see y twice, I want to get everything to the point where I can be able to factor out the y and then divide. So I have this. So here's our inverse, except I need to, of course, do my inverse notation. Here it is. Here is my inverse. Take a look. Okay. So my point about the domain and range, if you look at this function, it is rational. Its domain, we've talked about this with rational functions. you should always kind of assume that the domain is everything, and then you just think about any restrictions. So domain here is everything, except we have a rational function, domain cannot be 0. We can see pretty quickly that there's only one value that would make the denominator 0. So x cannot be equal to -4. So that's our domain. What we're saying here at the bottom of this page, again, the note that you see at the bottom of the page tells us that now, just by knowing that, I know that the range of this inverse is y, because range is y, all y cannot be equal to -4. Okay, so without doing any work, I just know that, because I know that it has to be the opposite. It has to be the domain of the range of the inverse is the domain of the original. So typically, a lot of students have trouble with the range of functions. And it's understandable, and especially for something that's rational like this. We talk more about the range in the future based on something else that we do. But I'm going to tell you kind of a straightforward way to make it happen. If you know the domain of the inverse, you know the range of the original. So by looking at the inverse function, we can see it's also rational. And the only issue that we're going to have with that is, again, something that makes the denominator 0. We can see really quickly that the value that would make the denominator 0 is 2. So because of that, that becomes our range, just using y, that y cannot equal 2. So if you're ever having trouble finding the range of a function, find its inverse, if you can, and see if there's an easy way to then determine what the domain of that inverse is, because then you know the range of the original function. Okay, so now here's one more. So notice, you should recognize that this is a square root function. Hopefully you did notice that. That is a square root function. And I actually have the line y equals x here already for us. And I also have the function itself in red, because I want to show you. So if you follow, you can pause if you want and first find the inverse. We only see x once, yay. So we're going to switch those up. We're going to square both sides. That's going to free us from that square root. We'll have x squared minus 6. I'm now trying to solve for y. And I'm going to write this just as two pieces here. So x squared over 3 minus 2. Okay. So that is what we're getting. So we might say, oh, okay, so that is x squared over 3 minus 2. But some of you might be saying, but that's a parabola. And you know that parabolas are shaped like this. And we've already looked at a parabola, and we can see very quickly that it doesn't pass the horizontal line test. So this is one of those situations where this does have an inverse, but it would require us restricting our situation here so that we only have basically half of that parabola. So if we think about the domain of our square root function, and we can set the inside equal to greater than or equal to 0. You can also look at the graph here. We can see that the domain is all values of x. You can see that x has to be greater than or equal to -2. You can see also pretty quickly, this is a square root function. We can't take the square root of a negative number. So we can see that -2 makes our function 0, and we do get the square root of 0, and then any value that's greater than or equal to -2 is going to give us a positive number. So our range here is that y needs to be greater than or equal to 0. So what I'm saying is this inverse that we found is in fact the inverse, as long as the domain is, of course, the range of our original, and the range here is the domain of the original, of course, with y. And as long as we have that, as long as that's the domain and range, you are good. You are good. That is your inverse. So taking a look at our graph here, I'm going to go to green so we can see. Well, let me come back here just to make sure you understand that this is f of x right here. So what we're going to do is we're going to draw the inverse, and I'm going to do this really easily. I'm not going to use my inverse function. I don't have to, just because I have the original already graphed. I'm just going to take each point that I see, so any kind of nice point that I see, and I'm just going to flip it because we know that that's true. So I have negative 2, 0. So I'm going to have 0, negative 2. So that's going to be where I start. Other points that I like, I see 1, 3 is a good point. So I'm going to put 3, 1. What else do I see? What else do I see? It looks like I have 6, 5. So I'm going to do 5, 6, like that. And then what you want to understand is that there is that symmetry. So there should be an aspect of like the similar shape here, because it needs, like, basically every point is symmetric over the line y equals x. I'm just not going to draw them all. So I just want to kind of create something that looks like I know that they do that. All right, well, this is what I was able to come up with, y'all. So here's our inverse function. Again, you can easily do this by actually putting points into that original that we have there. But you can also do it the way that I have it there, which is just trying to find the symmetric points from the original and putting those in. So we've learned a lot about inverses here. The notes at the bottom are what stuff I've already said, which is that the domain and range are flipped on the original and the inverse. And again, what I already said is if you have trouble finding the range of a function, find the domain of its inverse, and there you go. That'll make it easier for you. So that is section 2.8.